Today we're going to be looking at balancing equations. So far we've been writing skeleton equations, which are just the bare bones equations, and today we're going to talk about how we can add some numbers to that to make whatever we have on one side of our equation equal what we have on the other. Because there's this law that everything has to follow called the law of conservation of mass. And it's exactly what it sounds like. If you conserve something, you save it or you keep it. So the law of conservation of mass means that the mass will stay the same. It will be kept the same across the reaction. And so the total mass of the reactants must equal the total mass of the products. And sometimes when we carry out a chemical reaction, it might look like we have less after the chemical reaction. But we have to remember that a lot of times there's going to be a gas formed, and that's going to go out into the air, and we're not going to be able to actually see that. And if it's allowed to just escape out into the atmosphere, it's not going to be measured on our balance if we have it on a scale. So if we can collect all of that gas that's being produced, it will keep the same mass across the reaction. And the way that we show that our material is following that law of conservation of mass is by writing a balanced chemical equation. And that's where the number of atoms of each element is the same on both sides. And we've already been using subscripts. Remember, sub means below and script is writing. So the subscript is the small number that's in the lower right hand of a chemical symbol. And that's going to give us the number of atoms of that element within the compound. So whenever we have water, H2O, that small 2 is our subscript. It is telling us that in a molecule of water, H2O, we're going to have 2 hydrogens paired up with 1 oxygen. That's within the compound. If we look at a coefficient, that's going to be a larger number. It's going to be the same size as the chemical symbols that we're writing. It's placed in front of a symbol or formula, and it's going to indicate how many atoms or molecules of that substance are involved in the entire reaction. So again, that's how many atoms or molecules are involved in the reaction. So if we had 3 H2O, then this 3 out front is our coefficient, the same size as the capital H and the capital O, and it's saying that we have 3 water molecules. So we're going to practice adding in those coefficients to make sure that what we have starting out in the reaction, the reactants, will equal how much of our product we have. So we're going to be focusing on this arrow that's in the middle of our equation. And something you might do to help you out is kind of draw a line along where that arrow is to separate our reactants from our products. And we're going to list the elements that are involved on both sides. So hydrogen and oxygen are the 2. And I would write them in the exact same order on the product side, because we're going to compare how many we have. And if we put them in the same place, then we'll be able to more easily compare them. So hydrogen, we start out with 2. And oxygen, we see that we have 2. We're getting that from looking at those numbers right there. And when we look on the product side, within the molecule, I'm going to have 2 hydrogens. But then oxygen doesn't have a number right here. So remember, that means that there's going to be only 1 of them. Okay, now we need to look at our numbers and see what does not match up. So the hydrogens, we have 2 on both sides. That's good to go. But the oxygen, it does not match. We have 2 on the reactant side, only 1 on the product side. So the only numbers we're allowed to write right now are going to be numbers in front, our coefficients. And it is very helpful to go ahead and draw a little dash in front of each element or compound so that we know we have to come up with a number to go there. So the only way that I can get the oxygen on the product side to be the same as on the reactant side is to multiply it by 2. In every case here, we're trying to find a number to multiply by. We cannot add, it's only multiplying. So if I take that oxygen and I put a 2 in front, that's going to change it to where I have 2 oxygens. But the thing, when you have molecules, you can't just change one of the atoms. You have to change the entire molecule. That's why I had to write it in front of the water. And so not only did I change how many oxygens I have, Now I have more hydrogens. Whenever you look at this number and you also have a subscript, you have to multiply those to see how many of that element you have. So we take the 2 times 2, and now we actually have 4 hydrogen. So we fixed oxygen, but we messed up hydrogen in the process. And that's going to happen sometimes. That's okay. That's part of the process. We can fix it very easily because if we go back and look at the reactant side, we see we have 2 hydrogens. And if we want to have 4, we just need to multiply it times 2. And since they're separated over here, the only thing that we're going to change is how many hydrogens we have. And now if we compare, we have 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. Everything matches up. But we still have an empty blank in front of the O2. We're going to have some amount because if it was nothing, it just wouldn't be written down at all. So it's not going to be 0, it's going to be a 1. So when you don't need a coefficient in front to make it balanced, that means you're going to have 1 of that substance. So on the right-hand side, we're going to list the coefficients that we use, and we just separate them with commas. So we're going to have 2, 1, 2. I'm taking these numbers that are in front, the coefficients that we came up with, and just listing them. Okay. Let's try another one. We've got cobalt bromide combined with sodium phosphide to make cobalt phosphide and sodium bromide. We have a double replacement reaction going on. Let's go ahead and separate it into the 2 parts. And I'm going to list the elements. Cobalt, I'm starting with 1. Bromine, I'm starting with 3. Sodium, I'm starting with 3. And phosphorus, I'm starting with 1. And I'm going to go ahead and list those elements in the exact same order. So I'm just going to copy it down. I've got CO, Br, Na, and P. And then just look at this side, the product side, and see how many of those atoms we have. So cobalt, we've got 1. Bromine, we look over here, we've got 1. Sodium, we've got 1. And then phosphorus, we look back and we've got 1. So we have 1 of everything on the product side. And then we just look and see what does not match. So we look at cobalt, we've got 1 on each side, it's good. If we look at the bromine, we start with 3, but we only have 1 on the product side. So we go to the compound that has bromine, and there in front of it, remember we can only write numbers in front, we need to multiply by a number so that it will equal 3. So we're starting with 1. 1 times 3 gets us 3, so we'll put a 3 in front. And that changes the bromine, but it also changes the sodium. We have to change them both. So now let's look and see what doesn't match. We fixed the bromine, so now we check the sodium. And we just fixed it. By fixing the Br, it fixed the sodium too. We had 3 on both sides. And then our phosphorus, we have just 1 on each side. So it looks like we just needed that 1 coefficient and we balanced the whole thing. But everything needs a number in front of it. And we probably should have written those before we started. But we're going to fill in a 1 for all of these that we have left. So when we list the coefficients that we're using, we have 1, 1, 1, and then the last one's a 3. And that is showing you that the matter is conserved across that reaction. Now, you can approach this, and some of you will be able to just kind of look at it and see what doesn't match up. We're still going to start with our dashes here. And you might be able to just look at it and see, well, what does not match on both sides. It's still kind of helpful to draw our line. And you can look at K. There's a K on both sides. That's good. You can look at I. And you can see we start with 1 I. But on the product side, it's I2. There's 2 of them. So we have to put a 2 out front. And now we already checked K, but it changed it. Now it's K, and there's 2 of them. So then we look on our product side, and we fix that by just putting a 2 there. That gave us 2 of the fluorines, and looky there, on the reactant side, we have 2 fluorines. And so you might be able to kind of go through it like that, and on every single one of them not have to write all of the elements involved. But it's still helpful, especially if you're still having a little bit of trouble with it, to go ahead and list those out. So we're going to go ahead and work this one again. If that was confusing to you, that's a-okay. We can completely work it like this every single time. We're just going to list what we start with. We're going to have 1 potassium, and we're going to have 1 iodine, and then we're going to have 2 fluorines. And then I'm going to go ahead and write them in the same place. We've got K and I, and then over here we'll put F. And then check and see what you actually have on the product side. K, I have 1 of them. I have 2 of them. And then fluorine, I've got the 1. And then you look and see what doesn't match. So the first thing I see this time when I'm looking at it is that fluorine doesn't match. It really doesn't matter what you start with. I'm just going to go with the fluorine, and I see I have 2 on the reactant side, and I only have 1 on the product side, so that means I need to multiply it by 2. Remember, we are not writing it down here at the bottom. We are not adding on any subscripts. We are only writing coefficients out in front. So in changing how many fluorines we have, we also changed how many potassiums. So normally I just go ahead with whatever the last thing was that I changed, I go ahead and check that. So I changed potassium to 2, so I go back and look on the product side, and I only have 1. So that means I need a 2 in front. So that's going to change that to a 2, and it changed the I to a 2. So then check the I. Iodine I have 2, and on the product side I also have 2. So it looks like we have 2 of everything. It's all balanced, and we still have 2 open spots. So in those open spots we need 1s. 2, 1, 2, 1. Those are the coefficients that will balance the reaction and show that it's following the law of conservation of mass. Okay, let's look at another one here. We've got an addition reaction between iron and oxygen, forming iron 3 oxide. And we're just going to list what we have. Iron, we start with 1. Oxygen, we start with 2. And then we'll write them in the same order, and it just so happens it works out that way on the side too. Fe, we have 2 of them, and oxygen, we have 3. Now, let's go ahead. Most of you would probably see that the first element doesn't match. Iron, we only have 1 to start with, but we end up with 2 at the end. So let's draw our little dashes for our coefficients to go in, and we would need to multiply the iron by 2 in order to get that to match up. And then when we look at our oxygen, we have 2 and 3. And if you think back to what we do with charges when we have 2 and 3, we make them both equal 6. And we're going to do the exact same thing here. So if we have 2 oxygens on one side, we're going to have to multiply it by 3. So we have a total of 6. And then we do the same thing on the other side, only instead of multiplying it by 3, we're going to multiply it by 2. And that's 2 times 3 for a total of 6 oxygens. But when we put that 2 out front of our iron 3 oxide compound, you'll notice that it changed how many irons we have also. Now we have 2 times 2, or a total of 4 irons. We already wrote a 2 over here, but now we know that it's not actually going to be a 2. Then we need to change that. And instead of having a 2 out front, we actually need to have it be a 4. And now if we check iron, we have 4 on each side. Oxygen, we have 6 on both sides. That'll happen sometimes where you fix something, and then later on, whenever you put a coefficient to fix something else, you end up changing what you already fixed the first time. So it doesn't happen all that often, but ever so often you'll run across that. It doesn't mean that you did anything incorrectly. It just means that we had a little bit of extra work to do on it. Now, once you've seen that a few times, you might kind of be on the lookout for whenever you have 2 oxygens on one side and 3 on the other, because that's whenever this situation will occur most often, where you change it and then you have to go back and change it again. So anytime you have 2 of something and then 3 of something, you're going to have to make them both equal 6, more than likely. It might be that you have to make them be even larger numbers, but you could find that out by looking and making sure everything else is balanced. Now, in this one we have a double replacement reaction. And let's go ahead and start by drawing our lines for our coefficients and separating it. Now, this has something different than what we've been looking at so far. So far, we've just been looking at either single elements or a compound that's made up of only 2 different elements. Now we have those polyatomic ions. We have PO4 and NO3. And I want you to make a little note here that if a polyatomic ion is on both sides of the reaction, keep it together. That means you're going to look at it like it's a single entity, a single thing. So since we have PO4 on the left and we also have PO4 on the right, then we write it down like it's one thing. Whenever you have a polyatomic ion on one side and you don't see it on the other side, that's when you break it down to the individual elements. So if we didn't have PO4 on the product side, we'd have to look at P and O as two separate things. But we can go ahead and list what we have. Sodium, we're going to have 3 of them. And then again, since phosphate is on both sides, I'm just going to write down PO4, and I'm going to have 1 of those. Because it's not in parentheses, we know that we have only 1. Our other reactant, we have silver, just 1 of them. And then, again, nitrates on both sides, so I'm going to say I have only 1 of those. You do not separate it into the nitrogen and oxygen. So I'm going to go ahead and list them in the exact same place. I've got Na, PO4, Ag, and NO3. I know it might be tempting to kind of rearrange them based off of the location of the elements on the product side, but if you keep them in the same place, it makes it much easier to be able to compare. So if we look at how many sodiums we have on the product side, we've got the 1. How many phosphates do we have? We have only 1. How many silvers do we have? We've got 3 of them. And how many nitrates do we have? Only the 1. So now we need to look and see what does not match up. So Na, we start with 3, and then we end up with only 1. So that one right off the bat needs to be fixed. And the way we do that is to multiply 1 times 3. So we go and we find the compound with sodium in it, and we put a 3 in front. And that'll change that. But it also means that now, instead of having 1 nitrate, I'm going to have 3 of them. And I go ahead and just look at that one. In O3, I've got 3 of them. But back on the reactant side, I only had the 1 right here. So that means I need to put a 3 in front. That fixes that. And it also gives us 3 silvers. So check the silver. I have 3 of them. On the product side, I have 3. And we haven't touched phosphate yet, so be sure you check everything. PO4, we have 1. And PO4, we have 1. All of our numbers match now, but we still have 2 blanks. Remember, those get 1s. So our coefficients that balance the reaction are 1, 3, 1, 3. We have another similar looking reaction here, another double replacement. Let's go and draw our lines for our coefficients. Separate it into reactants and products. So we start with 10, and we have 1 of them. And then we have that ClO3, another polyatomic ion. So check and see if it's on the other side. And it is. We've got ClO3 right there. So that means we're going to keep it together. And if we look outside the parentheses, we see that we're going to have 4 of those on the reactant side. Then we've got potassium with 3 of them. And then we've got PO4. So check and make sure PO4 is on the other side as well. And it is. So we'll keep it together. The 1. And then we're going to list them in the same places over here. So we're going to write that we have SN, ClO3, K, and PO4. And we're just going to check that and see how many we have on the product side. 10, we're going to have 3 of them. ClO3, we have just the 1. K, we have 1. And then PO4, we're going to have 4 of them. So then we're going to compare and see what does not match up. So start with the first one, 10. I've got 1 on the product, or 1 on the reactant side and 3 on the product side. So I'm going to put a 3 in front of the compound with the 10, in order to fix that. But in doing so, I changed how many chlorates I had, ClO3. I did have 4, but by putting a 3 in front, I have to do 3 times 4. So now I actually have 12 of them. So go ahead and look at the product side and see how many we have over there. And we only have 1. So that means that we go and we find the compound that has ClO3, and we got to put a 12 in front. Okay, we haven't seen numbers that big yet, but we can have them. So when we changed that, it also changed how many Ks we have, potassiums, to 12. But if we look back on the reactant side, we only have 3. So what can we multiply 3 by in order to get 12? We can multiply it times 4. So that'll fix the potassium, but it'll also change how many of those phosphates I have. Now instead of 1, I have 4, which, if we look over here on our reactant side, is how many we have there. So check your numbers again. We've got 3, 12, 12, 4. So it's all balanced. We have 1 missing spot, so we just fill it in with a 1. So we've got 3, 4, 12, and 1. And you always want to be sure that it's in the most reduced form. You're never going to have a list of coefficients that's like 2, 4, 2. Because all those numbers, you could divide it by 2 and reduce it. So whenever you have correctly balanced it, you're not going to be able to divide a number into all of them. Okay. Now, the last 3 that we have are combustion reactions. And they're going to be just slightly different. That's why it's important to be able to recognize when you have a combustion reaction. We're still going to put our dashes so that we can fill in our coefficients. And we're still going to separate it. But every time we look at a combustion reaction, we're going to follow the order of CHO. Carbon, hydrogen, oxygen. And we're going to write it in that order on both sides. Carbon, hydrogen, oxygen. And we start out with our fuel with 4 carbons and 8 hydrogens. And then we look and see that it's reacting with 2 oxygens. Now on the product side, as long as it's complete combustion and carbon dioxide is the product with water, we're always going to have 1 carbon, 2 hydrogens, and then a total of 3 oxygens because we have 2 right here and 1 over here. So together we have a total of 3 oxygens. And it's always going to follow that order, 1, 2, 3. Okay. Now, because oxygen is found in both of our products, we want that to be the very last thing we look at because we've got to get carbon and hydrogen fixed first. And then we'll look and see, well, how did that affect the oxygen and how much of that we're actually going to end up with. So let's fix the carbon first. Carbon, we start with 4. So we need to put a 4 in front of the compound with the carbon so that it's balanced. Don't worry about what it did to the oxygen yet. We're going to look at that at the end. Then you're going to fix the hydrogen. We started with 8. We already have 2. So think about what number could we multiply by 2 to get 8? And that's going to be 4. 4 times 2 gives us 8 hydrogen. Now that we have both of those balanced, go back and look and see what it did to the oxygens. Okay, in this one, in the carbon dioxide, we had 4 times 2, which is going to give us 8. And then on the water, we have 4 times the 1, which is going to give us 4. Okay, so together, we have a total of 12 oxygens on the product side. And if we go back and look at the reactant side, we only have 2. So what could we multiply times 2 to get 12? That's going to be 6. And that will give us the 12 oxygens that we need. And you can see we still have a blank spot. So that means we're going to start with 1 of our fuel. So our coefficients for this complete combustion reaction are 1, 6, 4, and 4. Okay. Next one, also combustion. So we'll draw our line, draw our little dashes for our coefficients, and list CHO. CHO. Carbon, we start with 2. Hydrogen, we start with 6. Oxygen, we start with 2. And then on the product side, it's going to be 1, 2, 3. Make sure the carbon is balanced first. We need 2 of them, so we'll put a 2 out front. For hydrogen, we need 6, so 2 times 3 will get us that 6. And then look and see how many oxygens. Look and see how many oxygens we have. We've got 2 times 2, so we've got 4. We've got 3 times 1, 3. So whenever we add those together, we no longer have 3. Now we're going to have 7. Can we take 2 and multiply by a number and get 7? Not a whole number, we can't. It would be 3.5, but we can't write 3.5 as a coefficient. We can only write whole numbers. So that means what we're going to have to do, and this is what you always do if you end up with an odd number of oxygens on the right-hand side, since we can't divide it by 2, we go ahead and write that number down. We go ahead and write down that 7, which is going to give us 14 oxygens, which means then that I pretty much have to double everything else. Okay? So instead of a 2 right here, I really want it to be a 4. And instead of a 3 right here, we want it to be twice as much. We want it to be a 6. And instead of the 1 that we would have written out front, we're going to double it and make it be a 2. So when you get an odd number of oxygens right here, you take this number and you write it in front of the oxygen, and then every other number you have, we're going to cross it out, and it's going to be twice as much. And if you check and see what we have left now, carbon, we're going to have 4. Hydrogen, we're going to have 12. We already figured out the oxygen. So now on the product side, carbon, we have 4. Hydrogen, we have 12. And oxygen, we've got 8 plus 6, which is 14. And it matches. So we are going to have 2, 7, 4, 6. Okay, last one. Another combustion. Let's draw our lines. And we're going to list CHO, CHO. Carbon, we start with 5, hydrogen 10, oxygen 2. On the product side, 1, 2, 3. So to balance the carbon first, we put a 5 in front, changes that to 5. To balance the hydrogen, we need to end up with 10, so we do 2 times 5 and get 10. And then we look and see how many oxygens we have. We have 5 times 2, which will be 10, plus 5 times the 1 gets us 5. So we get 15, which is odd, and that means that that number goes right here. And every other number that we have has to be doubled. So our coefficients would be 2, 15, 10, and then 10 right there. And if you want to double check and make sure that everything's good, carbon, you can see now we have 10 of them. Hydrogen, we now have 20. Oxygen, we have 30. Carbon, we have 10. Hydrogen, we have 10 times 2, which is 20. And then oxygen, we've got 10 times 2, 20, plus 10 times 1 for a total of 30. And it all matches once again.